Hi everyone. Hopefully this video clears up any issues that you might be having and we can keep it concise and to the point. So a review of these topics, we talk about reaction rates, which is a study of some changing variable over time, usually in seconds, and we'll discuss why it's seconds and not minutes or hours later on. So our goals for this video cast will be to describe different techniques for measuring the rate of a reaction. So it's one thing to say what we'll measure, it's another thing entirely to explain how we will actually measure it. Then we'll calculate the change in a concentration for a reactant or a product and how that relates to the time that it takes to do that. In the middle, we'll understand that rates are not constant throughout a reaction, so they do change and it's not a linear relationship. Then we'll work on interpreting the slope of a concentration versus time graph and calculating average and instantaneous reaction rates. So with that being said, we'll start off with the study of chemical kinetics, which is the study of rates that a reaction occurs at. So it's usually measured in moles per liter per second, right, which is a change in concentration. You might see moles per liter abbreviated to the capital M, and that's just a short form for moles per liter. So it's not always in moles per liter per second. We can measure things in grams per second. We can measure in moles per second, just to name a few. We can also measure in liters per second if a volume of a gas is getting produced. So there's a lot of different ways to measure it, and the key is that we're measuring a changing variable that describes an amount over time. So to measure rates, we can't always rely on the data being given to us. We will have to obtain that data sometimes. And when we do, there are two key factors we aim for: time and one other variable, which we'll go through here a few of how to discuss or determine. So first, if a gas is either consumed or produced in a reaction, right, we can use gas displacement. So the idea is that a gas reactant in this beaker on the left, our gas will be produced, by a reaction, travel through the sealed tube and into this upside down test tube. Now, the more gas that gets produced, the more it pushes down the water in the tube, right? And the key is that it doesn't dissolve, or else the gas will end up traveling into the water and not generating a gas cavity. So the volume there can be measured right off of the side, and then we have a way of determining how much of a volume of a gas was produced, and then using gas laws, and usually the ideal gas law, right, which relates pressure, volume, the number of moles, temperature, and the gas constant to figure out the amount in moles of the gas. All right. So this is specifically when a gas is involved in the reaction. Now, if there's no gas, sometimes reactions have different colors, right? As an example of this, copper. Any copper solution is blue. Okay. Now, the intensity of the color is directly related to its concentration, and we measure that with a machine called a spectrophotometer. So the darker color a solution is, the more concentrated it is, which means there's more moles of the substance in it. The lighter it is, the more dilute or the less concentrated it is. So this number on the screen here measures a property called absorbance. And we call it absorbance of light. If the value is 100, right, that means it's absorbing 100% of the light in the sample and it's very dark. Right? None of the light actually passes through the machine. If the absorbance is 0, then we say the solution is clear, right? And it's approaching colorless because all light transmits through it, none is absorbed. So the darker it is, the higher the concentration, right? And there's a mathematical expression for that, and it's called the Beer-Lambert law, and we just abbreviate it as Beer's law more often. So A represents the absorbance, E and B are constants depending on the equipment that you're using, and C represents the concentration. So the higher the absorbance, the higher the concentration because it absorbs more light. And then at the bottom here, you can just see what the inside of a photometer looks like. So this technique is specific to solutions that have color to them, that change color, right? And then we can measure the change in concentration over the change in time. Now, for reactions that produce a gas specifically in an open vessel, and open means that the gas can escape. This is specific to gas as a product. The mass of the system will decrease over time. What that means is as the gas is produced, it escapes, right? And due to the law of conservation of mass, the mass will appear to go down. So by performing this reaction on a scale, you can measure this by measuring the change in mass over the change in time. And that gives us a rate, right? And we'll talk about how we can relate that to other substances later on. If you have an acidic or a basic compound as part of your reaction, you can measure the change in pH. So as the substance is used up or it's formed, the pH will change, right? And a digital pH meter will give you an exact value to 2 decimal places on the screen like you see there. And then by plotting that against time, you'll get a pH versus time curve, and we can relate that back to concentration of hydrogen ions. So everything relates back to concentration when we're working with solutions. Now notice the rate change on this graph. You can see how it's curved. So keep that shape in mind as we go throughout this lesson. Finally, we can measure the electrical conductivity, and that's just describing the concentration of ions. So the more ions that are in a solution, the more the solution will conduct, and a higher voltage will be read. Okay, so this, again, it's specific to solutions that have ions in them, and we're measuring voltage instead of concentration. So all of these techniques were ways of actually measuring a rate and being able to determine a value to use per second. So as an example, I'd like you to look at the reaction down here, designing a short test. And there's multiple answers for this. So what property would you use to measure the rate of the reaction? Pause the video, try it yourself. Right? Hopefully you paused and you're coming back to check the answer now. So magnesium reacts with hydrochloric acid. So magnesium is a solid, and the state is important here. Hydrochloric acid is an acid, so it's aqueous. Now this is a single displacement reaction. A metal plus an acid releases hydrogen gas, and then we have the other product left over still. Okay, so we'll balance it just as good habit here. And now, how can we measure it? So we'll just call these techniques at the bottom here. Right? So starting with number 1. Right? And again, if you haven't paused and tried this for yourself, I recommend you do it, and then see if we can come up with something that you said. So first off, you notice that a gas is produced. So we can use the change in mass. Right? Over time, the mass will decrease. So we have the mass in grams. Just put that there. And we've got the time of the reaction. So if you sketch a graph for this quickly, the mass will decrease until it eventually levels off when the reaction finishes. And then the mass will not change anymore. Okay? It will never reach 0 because there's still something in that beaker. It's the mass that's changing. Second, we could measure gas volume, right, into the test tube. So as this reaction proceeds, right, the volume of gas in liters versus time, it will slowly increase until it levels off, right? And when it levels off, we know that the reaction is finished. 3. Now, just really quick on that, it would not look like this, right? Because then that means the volume of gas approaches infinity and it doesn't stop changing. So we don't want that one down there. Finally, because we are working with hydrochloric acid, we can measure pH. And as this reaction occurs, we are losing the acid as it is turned into products. So when an acid is consumed, the pH becomes more neutral, which raises it towards 7. So it's going to slowly increase the pH until it levels off at some point of the pH. So you can see 3 different techniques for measuring the rate of the same reaction, right? And it's a matter of choosing the best equipment and techniques that you have available to you. So mathematically, let's calculate the rates here. So to calculate the change in concentration over time, right, you can see a formula here. We're going to examine this fictional reaction. A plus B produces C. The little letters here are the coefficients. Okay, and those come from a balanced chemical equation. So to determine the rate, it's the change in concentration of A. The square brackets represent concentration. A is the substance, over the change in time. And don't forget, when you see the triangle, it means final minus initial value. Right? Now, the second here, let's not get confused. These are just the units. So it's moles per liter per second. Now, these last 2 points here, okay, you can see there's a plus minus sign. When you're calculating the rate of a reactant, we use a negative sign, right? And the reason for that is the rate is always positive, right, in terms of its value. And we describe what happens. So if a reactant is being consumed and being turned into a product, its concentration is decreasing. So its final concentration is going to be lower than its initial. Well, when you subtract those two values, you'll end up with a negative number. And if you leave it as a negative number, the rate will be negative as well. So to compensate for that, anytime we find the rate of a reactant, what we're going to do is put a negative sign in front of it. For a product, we'll put a positive sign. Okay, so reactants, put a negative sign, products, put a positive sign, and that keeps our rate positive overall. Now, that's for calculating the rate of a single reactant that we have data for. Sometimes we'll get data for one substance and be asked to determine the rate of another. So we use this relationship here, which is fairly straightforward. Okay, so again, just to make a couple of notes, I'll go back to this slide here. Concentration is represented by the square brackets. Okay. Delta T represents time, and that's measured in seconds. Okay, and then the plus and negative sign. If it's a reactant, we use negative. If it's a product, we use the positive sign. Now, what is this representation here? So this is used to compare the rates of two different substances. All right, so you see lots of equivalent ratios here. You'll only ever be working with two of them at a time. So of this whole relationship here, notice how reactants have the negative sign in front of them and positives do not, so that holds true. Right? The little letters represent the coefficients from the balanced chemical equation. So by having coefficients and a measurable value together in a fraction, what we've really done is described a mole ratio. So this equation tells us that rates are proportional to the mole ratios, right, which is from your stoichiometry units in your grade 11 course. And that's all it's saying. So to compare, if you remember, or if we think back, ratios involve two substances, right? And this relationship here just states that you can make a relationship or equivalent ratios between any two substances in a reaction, whether they're both reactants, both products, or one of each. So what we want to note here, okay, just before we go on, is that the change in concentration of that substance A divided by time is equal to the rate, all right, of A. So in this case, what we can say, I'll just draw a little bit of a line here, is that negative 1 over A in this case times change in concentration over change in time. So this is just one component of the ratio, is really equal to 1 over A times the rate of A, right? And this component here factors in the mole ratio, right? As a little example for this, if I give us the reaction H2SO4 plus 2KOH producing K2SO4, so a neutralization reaction, right? And we describe the rate. So let's say we determine the rate of H2SO4, right? And we know what that value is. But what we really want to know is the rate that the potassium hydroxide, KOH, is produced at. What we would say is that that is equal to 1 over its coefficient, which is 2, times the concentration. Oh, we're just going to clean this up. Sorry, not concentration. 1 over the rate of KOH. Okay. And there's a negative sign in front of that. So when we go to rearrange that, right, and we go to solve for the rate of potassium hydroxide, we see that it's 2 times the rate of sulfuric acid is equal to the rate of potassium hydroxide. So the coefficients will tell you how the rates change relative to each other. If the coefficient's higher, the rate's higher. If it's a 1-to-1 ratio, then the rates are the same. And that's what this complex relationship is telling us, right? So hopefully that clears that up a little bit, and we'll go through a few more examples with that. Some important things to note is that rates are always written as positive values, and the description of the change is written after that. So we'll write the number and then whether something is being consumed or formed in the reaction. It is specific to each reactant or product, not the reaction itself. So we don't say the reaction is occurring at so many moles per liter per second. We say the reactant is being consumed or the product is being formed at a certain rate. Lastly, the most important part is that rates are not constant. They're fastest at the beginning and then they slow down. Okay, so you'll always see a graph either decreasing and leveling off or increasing and leveling off. And that leveling off tells you that the reaction is finished because the rate is 0. There's no more change. Okay, we'll look at this graphically now. So given a graph here, you can see 3 substances being charted, their concentration over their time. The slope of the line describes the rate. Okay, the reason for that is slope is rise over run. Well, in this case, rise is change in concentration, whereas run is change in time. And mathematically, that's equal to the rate. Don't forget, rise over run equals the slope, a very early relationship that you learn. Okay, so in this case, the slope is the rate. Right, so we can take it over any time interval. It would give us the average rate. If I measure from 0 seconds here to 400 seconds, I'd get the average rate of the reaction. Now, if I wanted to look at instantaneous rate, I would have to use a tangent line. Okay, so the average rate is equal to the change in concentration over the change in time. The instantaneous rate is equal to the tangent at that point in time. So at 100 seconds, for example, if I draw a tangent line, which is a line that touches just one point on the curve, and I calculate the slope of that line, that'll tell me the rate at that point in time. Okay, and why that's more accurate than the average rate is that the rate is always changing. So even though we determine the average rate for the whole reaction, right, it's not occurring at that rate at any given time. But the instantaneous rate is specific to a time point. So they each have their advantages. Now looking at that graph, you can see that the slope that I drew out is negative. So I want you to think, is that substance a product or a reactant based on the change in its concentration? Here's where you'll pause the video, think about it, and then resume. So if you did pause and you thought about it, the slope is negative, which means this is a reactant. Okay, it's losing concentration, and these two are the products. Okay, they start off at 0, which means there's nothing there, and they form. So if we were to write a reaction for this, NO2 is the only product producing NO and O2. And then if I were to balance that, we could do that there, and we were given the state of each. Okay, so the reaction graph can give us quite a bit of information for that. So that's the difference between average rate and instantaneous rate. All right, the average rate is calculated over a larger time interval, whereas the instantaneous rate is a tangent at one point in time. So I'll go through a couple of examples mathematically quickly. All right, there's our equations for these. So we'll outline these and we'll wrap this lesson up for us. So given this reaction here, I'm just going to make sure that we're not saving that. All right. We're being asked, what's the average rate of consumption of A? So the average rate is equal to the change in concentration of A over the change in time. So because A is a reactant, we should put a negative sign in front of it. Okay. Let's list our variables. The initial concentration is equal to 0.415 moles per liter. The final concentration is equal to 0.206. We were then given time as 14.7 minutes. Now that's too long of a time interval. We would never report a rate as something per minute because it's changing by the second. So we'll multiply this by 60, get 822 seconds, and now we can substitute those values in. All right, and we'll get an accurate average rate per second. So I'll take my average volume here, 0.026 moles. And you can see because it is a reactant, That change in concentration gives us a negative value, so we got to put the negative sign in front. Right? And when we punch that in, be careful with all of your negative signs. Okay, and you'll get a value 2.37 times 10 to the negative 5 moles per liter per second. Right? And it's not negative because you factored that out. So the average rate of A is equal to that there. Right? So that's using average rate when you're looking at a single reactant or product. Now, just as a little extension, right, looking at the mole ratio. If we look at A and B, B has a coefficient of 2 in front of it. A has a coefficient of 1. So the rate of B, if the rates are proportional to the mole ratios, that means the rate of B is going to be 2 times the rate of A. So for the rate of B, twice as large as A based on its coefficient, which will be equal to 4.74 times 10 to the negative 5 moles per liter per second. Right? So that's how we use that stoichiometry pattern, okay, instead to be able to find out those. Right? And now for our final statement, A is being consumed or used up at a rate of 2.37 times 10 to the negative 5 moles per liter per second. All right, very useful technique in terms of biology when you're studying enzyme activity as well as specific catalysts. So we'll wrap up with one more example here using that more complex one, okay, using the stoichiometry technique. So we're given a balanced chemical equation in the middle, and we're told that the rate of nitrogen dioxide is produced at 5 times 10 to the power of negative 6 moles per liter per second. So what is the rate of decomposition of N2O5? So here's where you'll use stoichiometry because you have the rate of one substance and you're looking for the rate of another. So because it's a product, 1 over 2, and again that bottom number is its coefficient, times the rate of N2O5 is equal to 1 over 4, the coefficient of N2O2, and the rate of NO2. So what we've created here is essentially a mole ratio. Right? If you don't like fractions, you can convert that to decimals. Right? Now we're going to ignore the negative sign here because the rate should always be positive. Okay. We're going to have the rate of N2O5 is equal to 0.25 times the rate of NO2. So when I isolate for that, right, I put 0.25 over 0.5 is R of NO2. Right, you can simplify that to 1/2. Right, so it's going to be 1/2 the value times that, right, and we're left with 2.5 times 10 to the negative 6 moles per liter per second. So that's the stoichiometric relationship. Once you know one rate, you know them all. For B, I'm going to show you a different way for this. For oxygen, okay, so it's a 4-to-1 ratio here. If we use a mole ratio instead, and a mole ratio was 2 equivalent fractions, where the first one, so 4 moles of NO2 over 1 mole of O2, that comes from your coefficient. The second fraction would be your rates. Okay, so it'd be 5 times 10 to the negative 6 moles per liter per second for NO2 over X moles per liter per second of oxygen. So by solving for that, you can see that essentially there's 4 times as much nitrogen dioxide as oxygen. So the rate's 4 times greater. In terms of oxygen, it's 4 times less. So what we can do here is to solve for the rate of oxygen, it's equal to this fraction. So just cross multiply and isolate for X, which is rate. Okay, so what we're going to have is 5 divided by 4, which is 1.25 times 10 to the negative 6 moles per liter per second. So you can utilize mole ratios and stoichiometry to determine rates, as well as just some common sense. Now it's not on here, but if we were to compare nitrogen dioxide to oxygen, you can see that there's 2 moles of N2O5 to 1 mole of O2. So the rate of oxygen should be half of the dinitrogen pentoxide rate, which it is. Okay, and you can see based on the numbers we have here, this is half of this value here. So I hope that helps. You can see the practice problems right below here with some answers in bold. Okay, you can pause the video if you don't have access to this and attempt those questions there. So I hope that helps, and good luck.